this is Honors Algebra 2 Pre-Calculus, and we're doing 1.5 in Algebra 2, which is scatterplots and least squares lines, which is just a fancy way to say best fit line. All right, so first let's address the elephant in the room. You should not realistically be drawing a scatter plot by hand in any super important situation. If you're a big-time scientist someday presenting data to like NASA and you walk in with a hand-drawn scatter plot, they are going to judge really hardcore, and they should. So nowadays you're probably using a computer or a calculator to make a scatter plot, right? To make it look polished, to make it look accurate. So realistically, there's no point in dwelling too much on drawing these things by hand. That said, if in the homework you're asked to draw a scatter plot by hand, I want to walk you through some of the things that you should know and sort of the basic 4 things that we would need to see on a scatter plot drawn by hand. Number 1 is a title, right? So whatever, if your x-axis is time in seconds and your y-axis is meters or is distance in meters, then I need you to write, maybe it's how far you've traveled in your bike, right? And maybe it's distance Tommy travels in his bike. Great. Cool. So, or distance that Susie travels in a canoe. I don't know, whatever it is, right? So label what is going on, right? So that's the title, right? Then you're going to label the axes, which goes back to what I just said about, like, maybe the x-axis is time in seconds and the y-axis is distance in meters, but you want to label the axes including units. And then scaling the axes. Now, this is an important point because the way that we scale axes often dictates how accurate our information is, right? So when you scale axes, what we're talking about when we talk about this idea of scaling axes, right, is that your x-axis, whatever your x-axis is, each one of these units of measure should be consistent. So if this is, let's say, 10 seconds, then the next hash mark should be 20 and the next one should be 30 because each of these is a distance of 10 seconds, right? So if this is like time in seconds, right? When we scale the y-axis, I don't have to go by the same distance, right? Maybe I'm going by ones because it's just about meters. So maybe we're talking 1, 2, 3, and this is my distance in meters, right? And this is, I don't know, Tommy's distance on a bike, right? I just made this up, but cool. All right, so notice the scales don't have to be the same, but they should be consistent within the specific axis. So the x-axis goes by 10 seconds, that's fine. The y-axis is going by 1 meter, that's fine. Now, another interesting thing can happen. Let's say we're talking about distance, let's say from home, and let's say at the start of the problem, let's say that maybe he's really far from home to be, like, he's never going to get close to home. Maybe he's really far away, right, on his bike. So maybe he's starting, like, I don't know, 100 meters away, right? And maybe he's riding away from home. Maybe as time goes on, he gets further away. Maybe Tommy's running away. Who knows? So then maybe I'm going 101 and 102 and so on, right? The reason I put this little jump here, right, you can use these little jumps if, for whatever reason, your data starts at a really high number, but you don't want to have to scale all the way up to 100. Like, I still wanted to go by ones, but I wanted to start at 100. And in this situation, the best way to do that is put a little jump in the axis. What you can't do, right, so what you can't do is you can't jump somewhere partway through. You can't be like, cool, that's 1 and that's 2, and then, oh, look, I'm going to have a sneaky little jump, and look, there's 100, right? You can't do that, right? So that if you're going to have a jump in your scale, it needs to be at the very start, so you jump from 0 to whatever other number is there, right? And then the last thing it says is plot the points within a certain degree of accuracy, right? Like, if our argument was that when 10 seconds in, he was a half a meter out, right? So, like, here, that's great. My half could be, it could be a 0.6. Who knows? That's fine, right? So if my point was something like 10, 0.5, it's got to be close to 10, 0.5. It shouldn't be up here. That would be wrong. But nobody's judging if your 0.5 is kind of a 0.6. Like, it's not a big deal. Graphing by hand and scatter plots by hand are really never going to be an important skill in your life. Cool. Still good to know how to read them, and good to know how to do them on a calculator or a computer. So we are going to do that as our second skill. We're going to talk about putting it on a calculator. Again, even if it's in the homework, don't panic. Nobody's judging your by-hand scatter plot drawing skills. If you can just make sure that you do all of these things, right? Plot the points somewhat accurately, make sure that you follow basic rules for scaling and labeling axes and have a title, you're going to be legit all good. It's not a big deal. All right. So, that's the first thing we're going to talk about, right? The next thing we're going to talk about is we're going to talk about how to enter some stuff into your calculator. So notice, let me just walk you through the 4 major topics we're going to go through. We're going to go through scatter plot by hand, which is basically this, not a big deal. Scatter plot on a calculator, we're going to use the TI calculator specifically, and that is way more useful, right? Best fit line, which your book also calls a least squares line. When we do it on a calculator, we're also going to call it a linear regression. We'll walk through that. And then we're going to talk about the concept of correlation. I actually think I might jump to correlation first because I don't conveniently have the calculator out right now, and I might do that in the second video. So we're gonna jump right to this topic number 4 and talk about correlation. So let's jump to correlation. So an important thing you'll learn if you ever take AP stats or anything of that ilk is that correlation and causation are not the same thing, right? So just because two things seem to have some sort of a relationship doesn't mean that one of them necessarily causes the other, right? So, for example, right, good example of this, right? So there's probably an argument that that people statistically with money fly in airplanes more often, right? Like if you have a lot of money, you probably fly in airplanes more often than someone who doesn't have a lot of money. The more often you fly in an airplane, technically, statistically, the more likely that you get an airplane accident. So if you were to actually plot like people that had crashed in an airplane versus wealthy people, you'd probably find that there are a lot of wealthy people that have crashed in airplanes because statistically speaking, wealthy people are more likely to be in airplanes more often. That doesn't mean that being rich makes you crash in an airplane, right? It doesn't mean that crashing in an airplane makes you rich. I guess it could if you sued and whatever. So point being, there's no causation. It just happens that being a very wealthy person and like being in some sort of an airplane accident might in some way be related because you are statistically more likely to be in airplanes more often and therefore up the probability that something could happen to you. But it's not causation of any kind, right? Okay, so here's what correlation looks like, right? So there's essentially 5 types of correlation, with one of them actually being none, like no correlation. So let's walk through this. So you can have what's called a positive correlation, okay? And you can have a negative correlation. And within both of those two categories, you can have something that's called strong, so a strong positive correlation or a strong negative correlation, and you can have something called weak, okay? So what a strong positive correlation looks like, okay? So positive correlation looks like this, right? So a positive correlation is basically as x increases, y also increases. So as the x values get higher, so do the y values, right? A negative correlation looks something like this, right? So as the x values increase, the y values decrease, right? The y values go down, okay? What makes it strong is it's almost a line. So you see how these look mostly lined up, right? See how these look mostly lined up? That's what makes them strong. So essentially the positive and negative refer the same way slope is, right? This line would have a positive slope, just like this correlation is trending positively, right? And this would be a negative slope. What makes it a weak correlation is that the dots are a bit more scattered, but there's still clearly a trend going uphill. So what makes it weak is it is more scattered, but still a clear trend. So there's still a clear trend that this is definitely going up. It's just that they don't make a nice happy line, right? And then a weak negative would look like this, where the dots are a little bit more spread out, but look, there's still a clear trend that they're going down. Now, I said that there were 5 types, and that's because the last type is no correlation, right? And that looks like just a bunch of random dots, right? Like no trend up, no trend, no trend up, no trend down, just, hey, look, there's a bunch of confetti on the floor, right? So when you talk about a positive or negative correlation, we're essentially talking about, so here's an example of something that's not causative, but there's a correlation. If you are taller, you tend to have a larger shoe size. It's not always true, right? But there is some correlation, and larger feet don't make you taller, and being taller don't necessarily make your feet larger, or doesn't necessarily make your feet larger, but there is some sort of a relation there that usually if you're taller, your feet are larger. Usually the taller you are, you weigh more, right? So like height and weight are things that have a positive correlation for most people. As you get taller, you gain weight, right? Now that's not to say that it's causative. It's not to say that if you're taller, you're automatically way heavier. But again, these are examples of correlations, right? So that's a positive correlation, right? Negative correlation, right? So example of a negative correlation means that as the x values increase, the y values get lower, right? So, for example, let's say that the x-axis was age, right? So as you get older, well, the y-axis might be something about a particular physical ability, right? It might be your ability to complete certain tasks, like the stupid presidential fitness test or whatever it is that we had to do in the 80s. So, like, maybe it's your ability to sprint a mile. Now, that's not to say that there isn't some guy in his 90s or some woman in her 80s that are, like, sprinting faster than I could ever run. But as you get older, your athletic ability in theory declines, right? That would be an example of a negative correlation. Again, that's not to say it's entirely causative, and sometimes sometimes there are causations, right? Sometimes getting older does, in fact, cause certain things, and there is causation, but again, correlation does not imply causation. That's not to say that some things aren't causative. There are definitely things that are causative. But just because two things seem to be related in some way does not necessarily mean that one causes the other. So, strong positive means goes uphill, right? Positive slope, and is almost a line. Strong negative means goes downhill and is almost a line. Weak positive means goes uphill but is kind of scattered. Weak negative goes downhill but is kind of scattered. And no correlation is all over the place. So there's a way that we can actually figure this out when we use our calculator, which is what we're going to do in the next video. And the way we do that is what's called an R value. So the R value, okay, so a perfect correlation, something that is completely and totally a perfect correlation, is that is a positive correlation. So with the R value, number one, the sign tells you positive or negative correlation, okay? So whatever the R value is, if the R value is a positive 0.7, that means we're talking positive correlations. If it's a negative 0.8, we're talking negative correlations. And then the actual numerical value, right, so the absolute value of R, if the absolute value is close to 1, then it's strong. And if the absolute value of R is close to 0, it's weak. Well, actually, so stronger the closer to 1, weaker the closer to 0. If you're very close to 0, sorry, I actually didn't mean to write below what you could see. If you're really, really close to 0, we're talking no correlation. So looking at an R value, so for instance, this might be an R value of like 0.9, sure, we'll call it 0.9, right? It's close to 1 and it's positive. This might be an R value of negative 0.93. It's close to negative 1, right? It's close to 1, but it is a negative number for a negative correlation. This might be an R value of a 0.7, right? It's farther from 1. It's getting closer to 0, so it's weaker, right? But it's still positive. This might be an R value of, like, I don't know, a negative 0.6, right? Because again, the negative says that it's a negative correlation. And again, I'm making up these numbers randomly, but just to show you the way that these R value works. And I'll show you how your calculator finds an R value when we do calculator stuff in the next video. So no correlation might be an R value that's something like 0.3, right? And you might be thinking, hey, this would be like a negative 0.3, because if you were arguing there was any trend at all, it would probably be down. But negative 0.3 or something like R equals 0.2, right? They're going to be values that are much, much closer to 0. And whether they're positive or negative is going to be a little bit subjective. Like, your calculator has a way to find it, but you might not be able to spot whether this is positive or negative because it's so loose that there's really no correlation. So again, fake R values that I made up, but that's sort of how correlation works. So if you're asked to describe the correlation of something, it really boils down to 5 possible answers. Strong positive correlation, strong negative correlation, weak positive correlation, weak negative correlation, or no correlation at all, right? And really, if you can see no pattern at all, it's pretty much always no correlation. So that's our first video. We'll do a second video where we learn some calculator skills, and we'll also graph some stuff by hand just to make sure you know how to do it.